Oh, good, good. Thank you. Thank you very much for that. So Magnus Karlberg, I'm professor in machine design at Luleå University of Technology then. So I'm here to talk about this, the AURO initiative and also the research vehicle platform that we have developed here. And hopefully we'll see you tomorrow at the excursion also, so you can view this machine and some other stuff there, and we do some demonstrations. So this Arctic Off-Road Robotics Laboratory, or AURO then, it's a collaboration between our university and then Swedish Cluster of Forest Technology and the Swedish University of Agricultural Sciences. We started to discuss how to make some initiative in this kind of making more, bringing in more of the autonomy in the forest sector, basically. So that's what we focus on our group quite a lot on, almost entirely nowadays. To do this, we quite early knew that we need some kind of equipment to actually test a lot of things. I mean, it's one thing to do simulations and work with small test pieces and all of that, but we wanted really to go to full scale immediately. So we had some need-finding sessions where we discussed with different, because this is a very multidisciplinary area. It's not just people like me that are interested in machine designs. It's also robotics people. It's, you know, people that knows about forest management and that kind of things. So we had a lot of workshops which ended up in the machine that you see here, which is a 10-ton machine. So it's a quite small to be a forestry machine. And it's not the machine that we foresee as the future, you know, vehicle that we'll see out in the forest. It's a platform for us to do research on, but it's large enough to test real test case. I mean, really be in the correct environment and work in correct scale, so we don't have to downscale everything. And which is very important because you have some special features happening when you go into full scale. So this machine, we basically have it fully sensorized, meaning that we have sensors for everything we need. We have, as I said, the full scale, we can work in the correct environment with this machine. And we also have quite a lot of data processing capabilities, which is required because everything happens in real time. So we will see some examples also in a bit. And it's also quite modular. We put also pendulum arms, as you can see, so we can work with drivability with different test scenarios and all of that. But we can also switch things. So if we don't work with a crane, we can put some other auxiliary equipment on the machine as well, quite easily. It's still a lot of work, but it's quite easy to do that because it's quite modular, this machine. Okay, then of course, in order to work in the correct environment, you need to go there, and you still need quite a good laboratory. So we have also built what we call the field laboratory. It looks like this, so we can bring the machine into this field laboratory, and then we can go out in the woods, so we actually work in the environment that we need to work, and then we pull it up with our truck like that. You will see all of this tomorrow, so we can actually have a decent, you know, working environment, although when it becomes quite, where we live, it's quite, you know, cold every now and then. And so basically that's the hardware structure, and you will not find too many other places in the world where they work in dedicated platforms like this in full scale. Then of course we work with simulations models in accordingly, because parts of the systems that we build relies on, as you see here, it's a kind of a CAD model, you could say, of the machine. And of course we do a lot of the planning stuff, and that happens in the virtual environment. So we work quite a lot with that as well. So let's say the total architecture consists of both the hardware parts, but also these virtual situations where we work in different systems with simulations as well. So I will talk about, just mention a few words about the area, some of the areas that are very important for us and that we have worked within in some of the research projects, and then we will demonstrate tomorrow, so we'll actually see some of these also. We have already seen some examples of the perception. Perception is, of course, if you remove the human from the machine, then of course the perception system becomes quite important. What you see as a human being has to be, you know, replaced by some sensor systems, and sensors are quite good today. Still, it's still very difficult to make the perception system robust. I mean, so that it works every time, not just every now and then when it's sunny, and it has to work when it's foggy, when it's rainy, when it's snow and whatnot. So perception system for any autonomous system, this is really, really, really important, both to be able to drive and navigate for safety reasons, to control your equipment. So it's really central beat. And of course, what we aim for is not to replicate the human, but to do more than the human can. Because of course, there are sensors today that can see much more than a human can see. We were into this different kind of, wavelengths that we are capable of seeing as humans, and others that we cannot see, that sensors actually can see. So there are good things with the sensors, but there are other things that are really difficult also with them. But of course, some of the things that we have been working on with the perception system is, of course, the topology of the surrounding environment, but also both stationary objects, we need to identify some obstacles, and also targets that we want to, for instance, pick up. But there also might be moving objects like, other humans and whatnot that you have to avoid. So both statical objects and dynamic objects. And what is really important, as I said earlier, is that it has to provide the information in real time. So you cannot basically take any state-of-the-art algorithms out there that takes forever to process. It has to happen 25 times every second or so. So real time is really important. Okay, this is some as we saw, we also work with bounding boxes. In this case, we have an example of finding stumps. We have been working, and then of course, not just in the image to find the stump, but we also want to position it in 3D so we know the extension of things. So it has to be mapped also into the 3D environment so we can use the 3D data of that. I think I have some, here you see also an animation to understand that this is really real time. We are just walking around and doing the detection here. And this is information fed to the system so that we can take decision. For instance, not to drive over a particular stump or stone, or if we want to really target something that we want to find in the environment also. So it looks like that. So real time again, very important. It's not always that you have bounding boxes is enough. This is an example of lichen where we try to find ways of not driving over that more than necessary. And of course, where should you put the bounding box? So here we use segmentation instead to find areas maybe where the density is a little bit lower of the lichen. So it's maybe smarter to drive there instead of right over. So this is just to find some good symbiosis between different ecosystem services out there, so that when we're doing some forest regeneration activities, we don't want to harm any other business in the woods, basically. So that's another example of perception. A little bit about drivability. Drivability is completely central, of course, if we cannot drive in the forest. And that's also why we are working with full scale. So the machine is, at least it's so large so you can drive in the actual environment. This is really, really difficult. I mean, it's probably quite difficult for a human to do this, and it's even more difficult to have a computer doing it for you. So, I mean, and the environment that we're talking about, it's really unstructured. You have a carrying capacity that really varies a lot in the environment, and the flexibility in the ground, you don't know what it is. So how do you take decision about that? I mean, the operators today, they have some experience, so they do this kind of decisions all the time. But that now has to be fed into a system that takes that just using the CPU, basically. We also have to understand the obstacles and know what to do. And here we also have heard of some examples about drones. We also need to know, should we take decision of what we see right now only? Or should we be able to trust something, for instance, if you fly over with a drone and you have some additional information about the environment? That's the kind of course, and you probably should every now and then. But it makes the decision strategies very different though then. And we have other problems like, what about the snow conditions? Today, as far as I know, there is very, very few sensors that have the capabilities to see a little bit around, both around the about the surface of the of the ground, a few decimeters down in the surface. But also if you have a snow, can you see below the snow? Probably not, and that's completely necessary to be able to drive in the snow in the future, probably. We have also low friction, of course, like ice situations and all of that. So we have been working a little bit with this to use the pendulum arm controls to be able to, have some good drivability. We, of course, have an anti-spin system. And then, of course, you can do the local planning. You don't have to drive in a straight line. You can, of course, change the planning as soon as you get some information about the environment. So that's the kind of strategies that we have tested today. This is, as far as I know, quite unexplored already, as for now still. You have a few examples, of course, but looking in this kind of unstructured environment, it's quite much to do still. So we are also working with that to some extent. Auxiliary equipment, I know that Pedro will talk a little bit more about this, so I will not talk so much, but we have been working basically so far in 2 different scenarios, and also Linnea has talked about the planting. So I will not go into so much details here, but I would like to show you the nice video from Hörnefors a few years ago, where we actually put a lot of different subsystems together and make the forwarding of a complete forwarding system here. So here you have the machine going forward, visualizing and finding this log here, so it knows where it is in space, and then the machine by itself goes forward, position itself in a position where it can pick it up, which is kind of a decent, distance from the crane. Then it lowers itself, and then basically, Pedro will talk about more about this, what the crane is doing, or things that he has been doing, as for instance in this case. But of course, we want to pick the log up and put it on the trailer there. And when we did this, as far as we know, nobody has actually done it. This is completely without the human then. So no one is running. We just put on kind of the on button, and then we release all the fingers. So all the different parts, and it's quite a lot to do this. Of course, it's not the fastest thing you have seen, but this is the first time you saw it. This has actually not been done before we did it, the whole cycle of the forwarding. So and the good thing of doing it is that now people know that it can be done. It wasn't the snow, a lot of snow here. It was quite flat. We know that. Still, it's been done. So, it cannot be stopped now. So, of course, we tested this a lot, and we have a paper, actually, it's not too far off that it will be published also about these scenarios. So it's a really, really nice situation. This was one, so it was a forwarding situation. And then we, of course, since this platform is quite versatile, we have been working in other situations where we use basically the same crane, but we put a little bit of different equipment on the tip then. So for instance, this is one example with an inverse site preparation mechanism, and also a completely new, as Linnea probably talked about, I wasn't here then, but a new equipment for site preparation and planting to do that simultaneously, which we tested on this machine. And this sequence you will see tomorrow. Oh, yeah. Good. So I think the final thing I will talk about is, and this is something that I'm kind of concerned about this issue, that when we now start to move the humans a little bit away from the machine and bringing more of the autonomy into it, then the question is, how should the machine look like? Should we just take the same machine and then we move the human and then there it is? I don't think so. I think we will see completely new concepts of forestry machines in the future. And you can just look at other fields, like in agriculture, and you have in construction equipment like the Volvo XH machine. Of course, if you remove the human from the machine, something happens with the concept. And of course, that should happen also in the forestry. We see electrification, we see automation and semi-automation in these fields. The question is, how will it be for us? I'm not so sure about electrification in terms of batteries. Maybe not. But there are some troubles in the forest doing this. But fossil-free, probably. I definitely foresee increased level of autonomy, smaller machines working together. I would think so. I don't know, but I think so. And I also think that we have machines that are capable of doing more things and much more precise in the future. And that also, and I think this is important, that then maybe we can start thinking about other ways of doing the work, not letting the machine restrict us to what we can do, but rather think what would be a good way here. So for instance, we have been working with some project about this lean concept that maybe why do you do the same everywhere? Maybe you should do a little bit different things every now and then, kind of that basic concept. So, and then you need machines like this that can do very precise jobs, work with different objectives, not just one objective for one ecosystem service, but for many at the same time. And maybe these autonomous machines can be an enabler for this. So I think that was basically what I had to say.
Thank you, Magnus.